The autumn rain fell in sheets across the Rechlin airfield on the morning of November 8, 1944, as Oberingenieur Klaus Becker watched a peculiar silhouette emerge through the low clouds. The aircraft's distinctive inverted gull wings cut through the mist, like no German fighter he had ever seen. It was not one of theirs. The Luftwaffe Technical Evaluation Center at Rechlin had become accustomed to examining captured Allied aircraft, but this particular arrival carried special significance. Word had filtered through intelligence channels about a new American naval fighter, one that British Fleet Air Arm pilots spoke of with unusual respect, and one that had begun appearing in limited numbers over Norway during carrier raids against German coastal installations. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Becker and his team were about to discover would fundamentally challenge their understanding of where Allied aviation technology had progressed, and more troublingly, how far German aviation had fallen behind. The aircraft before them represented more than captured enemy equipment. It embodied a philosophy of fighter design that accepted principles German engineers had long resisted, and it demonstrated industrial capabilities that Germany could no longer match even in theory, much less in practice. The story of how this particular aircraft came into German hands illuminates the complexity of the European air war's final years. Unlike the Pacific theater, where downed aircraft could be recovered from jungle islands, the European air war offered fewer opportunities for comprehensive enemy aircraft capture. Most Allied fighters shot down over occupied Europe crashed in contested areas quickly overrun by advancing Allied forces, or fell into the English Channel where recovery proved impossible. This Corsair's journey to Rechlin began not with a dramatic shootdown, but with a more mundane failure. On October 23, 1944, a British Fleet Air Arm pilot flying from HMS Implacable experienced engine trouble during operations off the Norwegian coast. Unable to maintain altitude, the pilot aimed for what appeared to be a clear field near Stavanger, still under German occupation. The landing, while rough, left the aircraft largely intact. German troops secured the site within hours, and the Kriegsmarine technical staff recognized the prize immediately. The recovery operation itself proved challenging. The Corsair weighed over 9,000 pounds empty, far heavier than most German fighters. Local Wehrmacht units provided a heavy transport truck and portable crane, working through the night to load the massive fighter onto a flatbed trailer. The overland journey to Rechlin took 5 days, travelling only at night to avoid Allied air attacks that had made daylight movement increasingly suicidal for German forces. When the aircraft finally arrived at the Luftwaffe's primary testing facility on November 8, the technical evaluation staff assembled with a mixture of curiosity and foreboding. Germany's strategic situation in late 1944 left little room for optimism. The Luftwaffe, once the terror of European skies, had been systematically destroyed through attrition, fuel shortages, and the relentless degradation of pilot training programs. The Western Allies controlled the skies over France, and American heavy bombers ranged across Germany with increasing impunity despite desperate defensive efforts. Every captured Allied aircraft now arrived not as a curiosity to be studied, but as evidence of an industrial and technological gap that seemed to widen daily. Oberingenieur Becker had spent the war years evaluating captured Allied aircraft, watching the evolution of enemy aviation technology with growing concern. He had examined early Spitfires and Hurricanes, studied captured P-38s and P-47s, and analysed the magnificent P-51 Mustang that had fundamentally altered the strategic bombing campaign's dynamics. Each captured aircraft revealed incremental improvements in Allied capabilities. But the accumulated weight of those improvements, combined with Germany's declining industrial capacity, suggested a trajectory that could only end one way. The initial inspection of the Corsair began on November 10th, once the aircraft had been moved into Rechlin's main hangar. The facility, once a showcase of German aviation technology, now bore the scars of repeated Allied bombing raids. Damaged hangars had been hastily repaired, critical machine tools relocated to dispersed sites, and personnel reduced, as skilled technicians were conscripted for infantry service or transferred to desperate jet fighter programs that consumed resources without producing meaningful numbers of operational aircraft. Becker's inspection team consisted of 12 engineers and technicians, a fraction of the staff that would have been assigned to such a project in earlier war years. They approached the Corsair with systematic methodology, beginning with external measurements and photographic documentation before proceeding to detailed component analysis. What they discovered in those first hours of examination would reshape their understanding of American naval aviation capabilities. The aircraft's sheer size immediately distinguished it from German fighter designs. The Corsair measured over 33 feet in length, with a wingspan exceeding 40 feet. More significantly, its empty weight exceeded 9,200 pounds, comparable to fully loaded Messerschmitt Bf 109 fighters. This weight disparity encapsulated a fundamental philosophical divide in fighter design that had evolved throughout the war. German fighter development had consistently prioritized performance through lightweight construction, accepting reduced protection and limited equipment to maximize speed and climb rate. The Messerschmitt Bf 109, backbone of German fighter forces, weighed approximately 5,000 pounds empty. Even the formidable Focke-Wulf Foe 190, considered heavy by German standards, barely exceeded 7,000 pounds empty. The Corsair's weight suggested either grotesque over-engineering or a completely different set of design priorities. Those priorities became evident as the inspection progressed. Behind the pilot's seat sat armor plate of hardened steel, thick enough to stop rifle-caliber rounds and shell fragments. The windscreen incorporated bulletproof glass panels significantly thicker than those in German fighters. Additional armor protected critical systems, including the oil cooler, fuel tanks, and engine accessories. The cumulative weight of protective systems exceeded 400 pounds, a penalty German designers had consistently refused to accept. The fuel system design reflected an obsession with survivability that struck the German team as excessive, even wasteful. The main fuel tanks featured self-sealing construction with multiple layers of rubber compounds that automatically swelled to seal bullet holes. German engineers had experimented with similar systems early in the war, but abandoned them due to weight penalties and manufacturing complexity. The Americans had apparently accepted hundreds of pounds of additional weight for enhanced survivability, a luxury Germany's fuel-starved Luftwaffe could scarcely afford even in concept. Becker's preliminary report, completed November 15th, noted these observations with clinical detachment, but his private correspondence revealed deeper concerns. In a letter to his wife, later recovered from family archives, he wrote, "We are examining an American aircraft that weighs as much as 2 of our fighters. Everything about it suggests they have fuel to burn, materials to waste, and industrial capacity beyond our imagination. We built fighters to win dogfights. They built fighters to win a long war." The detailed examination phase began November 16th with the systematic disassembly of major components. The Pratt & Whitney R2800 double Wasp engine became the immediate focus of intense scrutiny, and what the German engineers discovered fundamentally altered their assessment of American industrial capabilities. Engine specialist Hauptmann Friedrich Weber supervised the power plant examination, documenting every aspect of the 18-cylinder twin-row radial engine. The initial measurements shocked the assembled team. The engine produced over 2,000 horsepower at takeoff, nearly double the output of the Daimler-Benz DB605 powering late-model Bf 109s, and significantly exceeding even the BMW 801 radial in the W190. This power plant alone weighed more than 2,500 pounds, heavier than some complete German aircraft engines and their mounting systems combined. The engineering philosophy embedded in this single component revealed systematic American advantages in metallurgy, precision manufacturing, and quality control. Each cylinder featured forged aluminum heads with steel barrel liners manufactured to tolerances that German factories, by late 1944, could no longer consistently achieve. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Material shortages, worn machine tools, and the loss of skilled workers to military conscription had degraded German manufacturing precision across all industries. The Corsair's engine represented a level of industrial sophistication that Germany had possessed in 1940, but could no longer replicate in 1944. The cylinder cooling fins, machined with extraordinary precision and numbering in the hundreds per cylinder, demonstrated manufacturing capabilities that particularly troubled Weber's team. Maintaining adequate cooling in high-power radial engines required maximizing surface area, while maintaining structural integrity under enormous thermal and mechanical stresses. The double Wasp's cooling system represented solved problems that German engine designers still struggled with in contemporary designs. What truly alarmed the German evaluation team was the engine's serviceability design. Unlike German engines, which often required extensive disassembly for routine maintenance, the double Wasp featured quick-change components, accessible mounting points, and a logical arrangement that prioritized field maintenance. Weber calculated that a skilled American ground crew could replace an entire cylinder assembly in under 2 hours, a task that might require 8 hours with German engines given their more complex architecture and tighter packaging constraints. The supercharger system represented another technological achievement that highlighted diverging capabilities. The two-stage, two-speed supercharger allowed the Corsair to maintain high power output at altitudes where German fighters experienced significant performance degradation. The engineering team calculated that the Corsair could sustain combat power at altitudes exceeding 25,000 feet, giving it decisive advantages in the vertical dimension of air combat that had become increasingly important as Allied bomber formations operated at ever higher altitudes. Fuel injection rather than carburation provided another critical edge. The Corsair could maintain power in negative G maneuvers, something most German fighters absolutely could not do with their float-type carburetors. This seemingly technical detail translated to crucial tactical advantage. American pilots could push their aircraft into negative G dives to escape pursuing German fighters, while Luftwaffe pilots who attempted the same maneuver would experience engine cuts as fuel flow interrupted. German engineers had long understood this limitation, but fuel injection systems required precision manufacturing and quality control that Germany's degraded industrial base struggled to provide consistently. The propeller mechanism, a Hamilton standard hydromatic constant speed unit, demonstrated mechanical sophistication that German engineers recognized but could not replicate at scale. The system automatically adjusted blade pitch to maintain optimal engine RPM across varying flight conditions, reducing pilot workload while maximizing performance. German pilots manually adjusted propeller pitch on most fighter types, adding to already considerable task saturation during combat. Automatic systems existed in some German aircraft, but reliability problems and manufacturing complexity had prevented widespread adoption. Weber's engine analysis report, completed November 30th, concluded with observations that resonated throughout Rechlin's technical staff. The double Wasp represented not merely superior engineering, but the product of an industrial ecosystem that Germany no longer possessed. Advanced metallurgy, precision manufacturing, quality control systems, and engineering depth combined to create a power plant that Germany could not replicate, even if engineers fully understood every component. The industrial capacity to produce such sophisticated machinery at scale suggested an American aviation industry operating at levels Germany had never achieved even at its wartime peak. The implications extended far beyond a single captured aircraft. This engine represented one element of a comprehensive American naval aviation program that had fielded thousands of advanced carrier aircraft while simultaneously supporting massive land-based bomber and fighter production. Germany, by contrast, struggled to maintain production of existing designs with declining quality and chronic shortages of critical materials. The Americans were winning an industrial war that Germany had lost before the first shot was fired. December 5, 1944, marked the beginning of structural analysis, and the German engineering team's examination of the Corsair's airframe revealed design principles that fundamentally challenged their understanding of modern fighter construction in ways that went beyond simple performance. Metrics. Structural engineer Dippel. Ing. Hans Richter led the team methodically documenting every stress point, every load-bearing member, and every rivet pattern in the aircraft's skeleton. The comprehensive structural analysis revealed a fighter designed not merely for current combat requirements, but for evolution and sustained operations under conditions that German fighters were never intended to survive. The wing construction particularly fascinated and troubled Richter's team. The Corsair's distinctive inverted gull wing configuration was not merely an aesthetic choice or a clever solution to landing gear geometry, though it accomplished both objectives. It was a structural masterpiece that demonstrated American engineers' willingness to accept manufacturing complexity to achieve superior performance and strength characteristics. The wing's center section, where it joined the fuselage, was built like a bridge truss, with massive spars capable of withstanding combat maneuvers, generating forces exceeding 8 times gravity. Load testing data recovered from documentation found in the aircraft indicated the wings were certified for loads up to 11 Gs, forces that would structurally fail most German fighters. The Bf-109, optimized for lightweight construction, began experiencing structural failures at sustained loads above 7 Gs, and pilots were cautioned against sustained high-G maneuvers that might overstress the airframe. This strength came at substantial cost. The wing structure alone weighed nearly 2,000 pounds, but it enabled aggressive combat maneuvering that would tear wings off lighter aircraft, and it provided enormous resilience to combat damage. German pilots increasingly reported encountering American fighters that continued fighting effectively despite visible battle damage that would have grounded or destroyed German aircraft. The Corsair's structural over-engineering explained these troubling combat reports. The control surfaces exhibited similar robust design. Hydraulically boosted ailerons gave pilots the ability to execute high-speed rolls and reversals that would be physically impossible with manually operated controls at high airspeeds. German fighters retained purely manual control systems in most types, lighter and simpler, but demanding enormous physical strength from pilots during high-speed combat maneuvering. Luftwaffe pilots often reported physical exhaustion after extended combat, particularly at high speeds where control forces became nearly unmanageable. Perhaps most tellingly, the Corsair's structural design accommodated future growth. Mounting points existed for equipment not yet installed. Wiring harnesses included unused connectors. Structural reinforcements suggested the airframe could handle significant increases in engine power and equipment weight. The German team recognized this as evidence of a long-term development philosophy fundamentally different from German practice. American designers were building aircraft platforms designed to evolve and improve throughout production runs, accepting initial weight penalties for future capability growth. German designers, by contrast, optimized each aircraft for specific current requirements, producing fighters that performed well initially but offered limited growth potential. The Bf-109 had been in continuous production since 1937, but each attempt to increase performance through more powerful engines or heavier armament pushed the basic design closer to its structural limits. The Americans had apparently learned from this trap. The Corsair's robust structure meant that more powerful engines could be installed, heavier armament fitted, and additional equipment added, without fundamental redesign. This explained intelligence reports of Corsair variants with different engines, armament packages, and mission equipment, all flying from the same basic airframe. Germany's fighters, pushed to their design limits, offered no such flexibility. Richter's structural assessment report, completed December 20th, concluded with an observation that captured the essential difference in design philosophy. The Americans have built a fighter that can grow stronger. We have built fighters that can only grow weaker as we push them beyond their design limits. The Christmas season of 1944 brought little holiday spirit to Rechlin. Allied armies had liberated France and were pressing toward German borders. Soviet forces advanced relentlessly from the east. The Luftwaffe's desperate gamble in the Ardennes offensive consumed irreplaceable fuel reserves and accomplished little beyond delaying the inevitable. Against this backdrop, the technical evaluation of a captured American fighter seemed almost an academic exercise, documentation of technological superiority for historical record rather than actionable intelligence. Nevertheless, the examination continued with Teutonic thoroughness. December 27th marked the beginning of weapons systems analysis and what the German team discovered reinforced their growing understanding of American design priorities that valued combat effectiveness over weight savings. Weapons specialist Hauptmann Otto Schneider supervised the detailed examination of the Corsairs' 6 Browning M2 50 caliber machine guns. His reports conveyed technical admiration mixed with recognition that Germany had lost the armament philosophy debate years earlier without realizing it. The sheer weight of the armament installation shocked engineers accustomed to German fighter weapons. The 6 machine guns, mounting hardware, ammunition feed systems, and 400 rounds per gun totaled over 800 pounds, more than the entire armament package of early war Bf-109s, including guns, ammunition, and mounting structure. Each Browning M2 weighed 64 pounds empty, and the ammunition load alone exceeded 400 pounds. But this weight penalty purchased devastating offensive capability that German fighters could not match. The 50 caliber round, firing a projectile weighing approximately 700 grains at muzzle velocities approaching 3,000 feet per second, delivered kinetic energy more than double that of the rifle-caliber weapons equipping early German fighters. Even the heavier cannon armament increasingly fitted to German fighters offered different rather than superior capabilities, trading rate of fire and ammunition capacity for shell explosive content. The rate of fire multiplied this destructive potential. Each gun cycled at approximately 800 rounds per minute, meaning the Corsairs' combined battery could deliver 8,000 rounds per minute over 130 rounds per second into the target area. Schneider's team calculated that a 1-second burst placed nearly 250 projectiles into the air, each capable of causing catastrophic damage to aircraft structures. German fighters, by contrast, typically mounted combinations of machine guns and cannon with mixed ballistic characteristics. The Bf-109 G6, standard late-war variant, carried one 30mm cannon firing through the propeller hub and 2 13mm machine guns mounted above the engine. While the 30mm cannon delivered devastating explosive shells, its slow rate of fire, approximately 450 rounds per minute, and limited ammunition capacity, perhaps 60 rounds, meant that German pilots had perhaps 8 seconds of cannon firing time before exhausting ammunition. The Corsairs' ammunition capacity shaped combat persistence differently. With 400 rounds per gun, the aircraft carried enough ammunition for approximately 30 seconds of firing time, deliberately limited to encourage fire discipline according to American gunnery doctrine captured in technical manuals. But 30 seconds of firing time with 6 heavy machine guns provided far more combat persistence than German mixed armament with its precious cannon ammunition exhausted after brief bursts. The gun mounting system revealed American attention to practical engineering considerations, often sacrificed in German designs pressed for weight savings. The 3 guns in each wing were staggered to accommodate ammunition feed chutes, with outer guns mounted slightly forward of inner weapons. This arrangement prevented feed system conflicts while concentrating fire at harmonization range, typically 1,000 feet, where convergent gun trajectories intersected to create maximum projectile density. Electrical firing systems rather than mechanical linkages provided reliability advantages. The simple trigger circuit eliminated mechanical complexity and potential jamming points while allowing rapid-fire cycling without mechanical delays. German fighters used pneumatic or mechanical firing systems that added weight and complexity while introducing additional failure points in the firing chain. What particularly troubled Schneider was the cumulative effect of these armament characteristics on combat tactics. German fighters with lighter armament and less ammunition needed to approach closer and hold firing position longer to inflict decisive damage. American pilots could engage from greater distances, fire shorter bursts, and still achieve destructive effects. This tactical advantage compounded the performance advantages already documented. The psychological impact of facing such concentrated firepower appeared in Luftwaffe combat reports with increasing frequency. German pilots described reluctance to press attacks against American heavy fighters, knowing that even brief exposure to return fire could prove catastrophic. This psychological erosion, combined with mounting losses, created a death spiral for German fighter units. The most aggressive, experienced pilots pressed attacks and died, Surviving pilots grew cautious, avoiding decisive combat, allowing American fighters and bombers to operate with increasing impunity. Schneider's weapons analysis report, completed January 5, 1945, posed a question that haunted German tactical planning. If we cannot match their firepower, their armor, their speed, and their production, what tactical options remain beyond defensive survival? The new year brought no optimism to Rechlin. Soviet forces had launched massive winter offensives in the east, and Western Allied armies prepared to cross the Rhine. The Luftwaffe's pilot training program had collapsed under fuel shortages and Allied interdiction. New pilots reached operational units with perhaps 30 hours of flight training, inadequate to survive against Allied pilots with hundreds of hours of experience. The gap between Allied and German aviation capabilities, already vast, widened daily as American and British production accelerated, while German output declined under relentless bombing and resource exhaustion. Against this grim backdrop, industrial production specialist Ing. Martin Koch arrived at Rechlin on January 10th to examine the captured Corsair from a manufacturing perspective. His expertise in aircraft production systems gave him unique insight into reading aircraft as products of industrial processes, and what he discovered confirmed Germany's worst strategic fears. Koch's inspection focused on manufacturing techniques visible in the aircraft's construction. Rivet patterns, joint designs, and assembly methods told stories about factory organization, worker skill levels, and production priorities. What he found both impressed him and deepened his understanding of why Germany was losing the industrial war. The Corsair was designed for mass production by semi-skilled workers in ways that German aircraft simply were not. The modular construction philosophy appeared throughout the aircraft. Major sections, fuselage, wing center section, outer wing panels, tail assembly were designed as separate modules that could be manufactured in parallel at different facilities, then transported to final assembly plants for integration. This approach enabled production scaling impossible with traditional aircraft construction methods. German aircraft typically required sequential assembly with extensive hand-fitting by skilled craftsmen. The Bf 109, despite years of production refinement, still required skilled workers to hand-fit many components, adjust tolerances, and make final assembly decisions based on experience rather than standardized procedures. This craftsmanship produced excellent individual aircraft, but made rapid production, scaling impossible, and complicated field maintenance, with parts that were not truly interchangeable. Standardization of fasteners and components revealed another American strategic choice. The Corsair used a relatively limited variety of bolt sizes, screw types, and fastener specifications compared to German aircraft, which often featured unique fasteners for different applications. This American approach simplified inventory management, reduced manufacturing complexity, and accelerated both production and field maintenance. Koch calculated that reduced fastener variety alone probably saved thousands of man-hours per aircraft in production time and substantially simplified supply chain logistics. The surface finish quality provided evidence of sophisticated manufacturing equipment operating with consistent precision. The aluminum skin panels featured uniform thickness, consistent dimpling around rivets, and precise edge preparation characteristics of stamping and forming equipment operating with tight tolerances. German factories, increasingly stressed by material shortages, worn equipment, and loss of skilled workers, struggled to maintain such consistency. The declining quality of German aircraft production had become a source of ongoing concern throughout the aviation industry. Interchangeability of parts represented perhaps the most significant manufacturing philosophy difference. Koch examined multiple supposedly identical components and found them truly interchangeable without hand-fitting or adjustment. Parts from the left wing could substitute for right-wing components. Hydraulic fittings showed no evidence of hand filing. Electrical connectors followed rigid standardization protocols. This interchangeability meant that damaged aircraft could be rapidly repaired using parts from other aircraft, and that maintenance personnel could service any Corsair without unique tools or procedures specific to individual aircraft. German production philosophy had evolved differently. The emphasis on craftsmanship and the tradition of skilled workers hand-fitting components to achieve optimal performance had created aircraft that performed superbly, but suffered from parts incompatibility and maintenance. Complexity. 2. BF-109s built in the same factory might have subtly different parts that could not be freely exchanged without adjustment. The material quality itself told disturbing stories. The aluminum alloys used in the Corsairs' structure exhibited superior strength to weight characteristics compared to German materials. Metallurgical analysis revealed sophisticated alloy formulations and heat treatment processes. German industry had mastered similar metallurgy earlier in the war, but by 1945, shortages of critical alloying elements and degraded quality control had reduced German aluminum quality to levels below pre-war standards. The steel components' armor plate, engine mounts, landing gear structures similarly demonstrated superior material science and quality. Control. Germany's steel production, never adequate for simultaneous armaments programs across all services, had declined under bombing and resource exhaustion. The quality variations in German steel production meant that ostensibly identical parts might have significantly different strength characteristics, forcing conservative design practices that added weight and reduced performance. Koch's most troubling discovery involved manufacturing tolerances. The precision evident in mating surfaces, bearing fits, and hydraulic connections suggested manufacturing equipment and quality control systems far more sophisticated than those available in German factories by late 1944. Maintaining such tolerances required not just skilled workers, but sophisticated measurement equipment, statistical quality control processes, and a manufacturing culture that prioritized consistency and precision over heroic individual craftsmanship. The production implications crystallized in Koch's final report, completed January 30, 1945. He estimated that American factories could produce Corsairs at rates 5 to 10 times faster than German factories could manufacture equivalent aircraft, assuming equivalent numbers of workers and factory space. But the comparison was actually more dire. American industrial capacity dwarfed German production infrastructure, meaning actual production ratios were far more lopsided. More troubling still, American aircraft production was accelerating, while German production declined. The Americans were building new factories, training new workers, and introducing improved production methods, while Germany's factories were being bombed into rubble, skilled workers conscripted for infantry service, and production dispersed into inefficient underground facilities to escape aerial bombardment. Koch's conclusion was inescapable. We are fighting an industrial war against an opponent whose manufacturing philosophy, technological base, and production capacity represent insurmountable advantages. The aircraft before us is not merely a superior weapon, it is evidence of industrial superiority so complete that military skill cannot compensate. February 14, 1945, brought the final scheduled evaluation session. Oberst Hermann Fischer, a veteran fighter pilot with over 300 combat missions, arrived to assess the Corsair from an operational perspective. Fischer had flown Bf-109s since the Battle of Britain, survived the Russian front, and accumulated enough combat experience to understand how aircraft characteristics translated to tactical effectiveness. Sitting in the Corsair's cockpit proved an education. The seat was larger and more heavily padded than German fighters, positioned behind substantial armor protection. The instruments were logically arranged, clearly marked, and included redundant systems for critical functions. An armored glass windscreen provided protection against frontal attacks that would kill or wound pilots in unprotected German fighters. The visibility surprised Fischer despite the large nose and engine cowling. The Corsair's cockpit sat high in the airframe, providing good forward and lateral visibility. The inverted gull-wing configuration actually improved the pilot's ability to see downward and to the sides during combat maneuvering. Only rearward visibility suffered significantly, though the Americans had addressed this with a rear-view mirror, a simple solution German designers had never systematically implemented. The control layout reflected a philosophy prioritizing pilot workload reduction. The constant speed propeller eliminated manual pitch adjustments. Hydraulic systems reduced control forces. Electrical systems automated functions that required pilot attention in German fighters. Fischer recognized that these design choices, while adding weight and complexity, allowed American pilots to focus more cognitive resources on tactical decision-making rather than aircraft management. Fischer mentally simulated combat scenarios, drawing on his extensive experience fighting American aircraft. The tactical implications became devastatingly clear. The Corsair pilot held initiative in almost every tactical situation. Superior speed allowed choosing when to engage and when to disengage. Superior climb rate enabled regaining altitude advantage after attacks. Superior firepower meant brief firing opportunities could achieve lethal effects. Superior protection meant surviving hits that would destroy German fighters. German pilots, by contrast, faced a tactical straitjacket, unable to catch fleeing Corsairs, unable to outclimb them, unable to survive their firepower, and increasingly unable to rely on superior maneuverability as American pilots learned to avoid turning fights. The Luftwaffe's fighter force was being systematically destroyed, not through decisive aerial battles, but through accumulated attrition that could not be replaced. The psychological dimensions troubled Fischer as much as tactical realities. Knowing you faced aircraft superior in almost every performance category corroded combat effectiveness. Luftwaffe pilots increasingly avoided combat with American fighters when possible, seeking easier targets or simply refusing combat. This natural self-preservation instinct, multiplied across thousands of German pilots, meant that American fighters achieved air superiority not through overwhelming numbers alone, but through qualitative superiority that made German pilots reluctant to engage. Fischer's combat assessment, filed February 22, 1945, included observations that his superiors found unpalatable. "We are asking pilots to fight an air war we have already lost. Every tactical advantage belongs to the enemy. Our pilots die not from lack of skill or courage, but because they fly inferior aircraft against opponents who control every aspect of engagement." Geometry. The final technical report on the captured Corsair was completed March 1, 1945, as Soviet armies approached Berlin and Western Allied forces crossed the Rhine. The comprehensive analysis, compiled from months of detailed examination, transcended dry engineering assessment to offer strategic perspective on what the captured aircraft revealed about the trajectory of the air war. The engineering team recognized that the Corsair represented not merely superior technology, but a superior approach to interconnected challenges of aircraft design, industrial production, pilot training, and tactical employment. American naval aviation had evolved into a comprehensive system where each element reinforced others, creating combat effectiveness exceeding the sum of individual advantages. The internal consistency of American design philosophy became clear through examination. Heavy armament required strong airframes to accommodate weight and recoil forces. Strong airframes enabled aggressive combat maneuvering and absorbed battle damage. Powerful engines overcame weight penalties while providing performance superiority. Pilot protection systems reflected a long war mindset, valuing experienced pilot survival over weight savings. Manufacturing design enabled mass production that could replace losses and continuously upgrade capabilities. German aviation, by contrast, reflected different constraints and priorities. Material shortages necessitated lightweight designs. Limited industrial capacity favored craft production over mass manufacturing. Short war assumptions led to sacrificing pilot protection for performance. The resulting aircraft, nimble, deadly in skilled hands, had proven devastatingly effective in the war's opening phases. But as the conflict evolved into attritional struggle, these design choices became fatal liabilities. The captured Corsair crystallized the industrial reality underlying the European air war. American factories produced advanced aircraft in numbers German industry could not approach while simultaneously developing next-generation designs. German production struggled to replace losses with aircraft of declining quality. The Americans were fighting a war of industrial attrition. They were mathematically certain to win, while Germany exhausted limited resources maintaining unsustainable combat tempo. The fate of the captured Corsair itself reflected the broader trajectory. On March 19, 1945, American heavy bombers attacked Rechlin in a massive raid that effectively ended the facility's operations. The captured aircraft was destroyed in the attack, reduced to twisted wreckage along with months of accumulated research data. The historical irony was not lost on survivors. The Americans could afford to lose the single captured Corsair because thousands more operated from carriers across the Pacific and in European waters. German engineers had analyzed it, hoping to find counters to its advantages, but the fundamental problems it represented, American industrial superiority, advanced technology, and systematic approach to air warfare, had no solution within Germany's constrained capabilities. The captured F4U Corsair's brief presence at Rechlin served as stark education in industrial warfare's realities. It provided a window into American aviation capabilities that revealed uncomfortable truths about the war's inevitable conclusion. The German engineers who studied it understood the implications, documented them thoroughly, and watched as their warnings went unheeded while the Third Reich collapsed around them. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.